the organizer for organizing this nice conference, and also for the invitation to give this talk. So yeah, today I would like to present a certain, sorry, I have a problem with my pencil. I would like to present a certain geometric or gauge theoretic approach to the spectral theory of a certain class of quantum mechanical operators, and then show some maybe more concrete application to the study of black holes. And most of what I'm going to talk about can be found in this. Okay, I cannot use the, I don't know. I cannot use the, okay, maybe now I can. No, you don't, okay. Anyway, most of what I'm going to talk about can be found in these works, which I did together with several great collaborators. Okay, so let me maybe start with some introduction and also a little bit of motivation. So one first point is the following. In general, we know that finding exact analytic solution for the spectral theory of quantum mechanical operators is extremely hard, right? We have some toy model that we like very much, and the standard example is the harmonic oscillator, where we can write down exact analytic solution for the quantization condition, the eigenfunction, and so on. But in general, this is much harder. So in order to make some progress in this direction, we needed to develop some new non-perturbative tools. And what we noticed during the last decade, more or less, is that basically, if we think of quantum mechanics from a geometrical point of view, similar in some sense to what Bailly and Parisi and Boros were doing in the 70s, then if we follow this geometrical approach, then we can actually make contact with supersymmetric gauge theory and also with topological string, and we can use tools and idea that we have been developing in this context to provide exact solution for a new family of operators. So what I would like to do today is the following. So in the first part, I would like to review some of the idea behind this geometric or gauge theoretic approach to spectral theory, and then show maybe more concrete application to black holes, and in particular, I will focus on the particular example of black hole. Now, from the point of view of spectral theory or quantum mechanics, black hole quasi-normal mode are like resonances or distribution. Okay, so we have like a discrete family of eigenvalues which have a non-zero imaginary part. And physically, these quantities are interesting because they encode the response of the black hole to a certain perturbation. And well, recently, this quantity also received a lot of attention because they also appear in the signal when we consider like the merging of two black holes. In particular, they are the responsible for this damped oscillation that we see in this final this ring down phase of the system. And one interesting aspect of this quantity is that if once we are able to measure them, then according to the no-head theorem, we can use that, for example, to determine the mass and the angular momentum of the final. And if we have enough precision to actually measure several of these oscillation frequencies, we can also use that to test this no-head hypothesis. Okay, so this was to introduce and motivate a little bit the various topics that are going to appear in this talk. Now I would like to go a little bit more into the detail, and in particular present some of the aspects behind this geometric or gauge theoretic approach to quantum mechanics. So a very important role in this approach is played by what are called the quantum fields. Okay, so these are, for example, the main building block which determine the exact quantization condition for the operators. Okay, so if we want to get exact analytic solution for the spectral theory of quantum mechanical operators, as a first step, we have to find exact analytic expression for this quantum field. So what I would like to do now is to introduce this quantity a little bit more in detail. And well, in order to do that, it's useful maybe to take one step back and start from the classical. So once we have a quantum mechanical operator of this form here, if we look at the classical counterpart, we can systematically associate to this operator a classical curve, which look like this. Where now x and p are just complex values. And today we will actually focus on a particular subset of operators, which are those such that the classical curve coincide with a four-dimensional SU2 cyber looping. And there are actually several interesting extension and generalization of this framework, which make contact with higher rank gauge theory or also higher dimensional theory. But what I'm going to say today apply to this particular subset. And because of this connection with cyber and looping, sometimes we refer to this operator as the quantum cyber looping. Now, one of the simplest but already non-trivial example, which is sometimes useful for pedagogical purposes, is the example of the modifier. So in this case, the relevant operator is given by this. Okay, so we have a Schrödinger type of equation with a hyperbolic cosine potential. And lambda here is like the strength of our potential. Now, when we look at the classical curve, basically we end up with the Cyber-Witten curve of the four-dimensional n equals to SU2 superunions. Okay, and from the point of view of the gauge theory, then lambda here is played the role of, it's like the dynamical scale of the exponential of the gauge coupling, and this instead is the Coulomb branch time. And then once we have this classical setup here, we also associate to this curve the classical periods, which are defined in this way. Okay, so this is the what is usually called the Cyber-Witten differential, and we integrate this differential over the corresponding sides. Now, once we have the classical periods, we can already get some intuition in the spectrum of this operator by using the semi-classical Bohr-sum of quantization. So in this setup, basically we are quantizing the classical phase space value, and the quantization looks like this, where n here is the quantum number and makes contact with the different energy. Okay. And in our framework, this classical volume is basically computed by the classical B period, which for this geometry we can compute explicitly in the particular example of the modifier material. For instance, this is given by this explicit expression here, where kappa and chi here are like elliptic integral of first and second kind. I think it says that the organizer has stopped the sharing. Maybe I can start again.
No, wasn't me.
Okay, can you see it again?
Yeah.
And okay, so this is basically the classical volume, and then this gives us already some kind of intuition on the spectrum. But it's known that in general, this semi-classical Bohr-sum effect quantization has to be supplied by additional quantum correction, which are both perturbative and non-perturbative in each bar. Now, the perturbative correction can be computed in a systematic way by using the Allorder WP. Okay. So in this method, basically what we do is that we make a perturbative ansatz of this form here. Okay. So this is a perturbative series in each bar. We plug it into the equation and we solve order by order each bar. And this is something that we can do in a relatively systematic way. And then we define the WKB period basically by integrating this perturbative quantum differential over the corresponding sides. And when we take n equals 0, this gives us back the classical period. But on the top of that, we have a full tower of perturbative correction in each bar, which are essentially these corrections. Now, as it happens very often in physics, when we do perturbation theory, we end up with the Bertrand series. Okay. And this is also the case here. So this is an asymptotic series with 0 edges of convergence. And if we want to get exact analytic answer, we need to find a way to assume this perturbative expansion. Now, before going into the resumation problem, let me just stress that this connection that we were observing at the level of the classical curve with this supersymmetric theory actually also persists at the WPB level, and a concrete realization of this connection can be seen, for example, from the fact that we can read the BPS spectrum of the underlying theory and also the corresponding central charge simply by looking at the singularity in the Borel plane of this WPB. So this is just to stress that the connection between these quantum mechanical operators and the supersymmetric theory is really something which is quite deep and that show up at various levels. Now, the point where this connection is really very strong is when it comes to finding an exact resumation of the WPB. Okay, so this is what we usually refer to for quantum periods. And by using four-dimensional gauge theory tools, which we can actually perform this resumation very explicitly. And there are actually several ways in which we can do that, depending on which problem we are interested in or which question we want to answer. There is one or another which may be more suitable. Now, today I will focus on one particular approach, which is the one that relies on the formulation in terms of four-dimensional omega background, and in particular, which goes back to the work of Nekrasov and Shatashvili. So a very important point in this approach is that basically we can map this very hard task of finding the resumation of this H-bar expansion in the WPB period. We can map this very hard question to something much simpler, which is how to compute the four-dimensional Nekrasov-Shatashvili image. And today, this is something that we really know how to do very explicitly. So if we go back to our example of the modifier material, for example, the quantum B period can be computed exactly and explicitly in this form here. So we have some log of gamma function, and then we are basically repackaging everything into this function f, which is the Nekrasov-Shatashvili image. And for the example of the modifier material, this is the free energy of the four-dimensional n equal to pure SU2 superluminous, which we already, this is the same gauge theory that show up at the classical level. Now, I think that probably the main point that I want to make here is that this quantity is not just some kind of abstract object that we don't really know what it is. In this four-dimensional framework, this is really a very concrete object which needs a proper definition and that we know how to compute very explicitly. And for the purpose of this talk, one important property of this quantity is that it's exact in H-bar, where H-bar, from the point of view of the supersymmetric gauge theory, play the role of the omega background. Okay. So thanks to this supersymmetric gauge theory technology, we can assign this WPB period and get an exact analytic expression for this quantum. And then once we have this, we can write down in a more or less direct way the exact quantization condition for the spectrum, which in the case of the modifier material look like this, where this is precisely the Nekrasov-Shatashvili image. Now, in the following, in order to stress that this is really a precise quantity that we can compute within this supersymmetric gauge theory framework, I will use this particular notation. Now, this is the example of the modifier material. But actually, there are much larger and maybe also more interesting class of operators which we can study and which have been studied in a similar way. And also here, I just focus exclusively on the quantization condition, but this approach can also be used to compute other objects in spectral theory, like the eigenfunction, the Freddie-Terman. Okay, so what I would like to do now is to apply this type of idea to the study of black holes, and more precisely, here I will focus only on this black hole. And okay, so this is the second. And to start with, we can start with the simplest example, which is the one of the four-dimensional Schwarzschild black hole. Okay, so in this case, the metric can be written explicitly in this form here. And in this convention, n is like the mass of our group. Okay. So this is a particular solution to the Einstein equation. And one maybe more or less natural question that we can ask is, okay, so we have the Schwarzschild metric, what happens if we add a small perturbation to this solution? And it was shown already a while ago by Reggie and Wheeler that linear perturbation of the Schwarzschild metric can be encoded in a relatively simple and also elegant second-order differential equation, which is the Reggie-Wheeler equation. Now, in order to derive this equation, it's convenient in some sense to exploit the symmetry of the problem and decompose the perturbation in something which looks more or less like this. Okay. So this is essentially a decomposition in terms of spherical harmonics, which encode the angular part. Then we also have the radial part and some time effects. Okay. And then when we take these ansatz and we plug this back into the Einstein equation, we obtain, and we do also some algebra and so on, we obtain the Reggie-Wheeler equation, which is this equation. Okay. So this is characterized by a potential, which looks like this. L here is related to this decomposition in spherical harmonics. And then we have the frequency here, omega, which comes from the fact that in the process we had some time derivative. And then we have the radial part, which is encoded in this quantity. Okay. So basically, this means that we can rephrase the problem of study linear perturbation of the Schwarzschild metric to study this Reggie-Wheeler equation. And for the particular setup of quasi-normal mode, this Reggie-Wheeler equation also has to be supplied by some appropriate boundary condition. And in order to maybe get a feeling of which type of boundary condition we want to impose, sometimes it's useful to introduce the tortoise coordinate in this way here. Okay. So what we are doing here, essentially, we are making sure that the horizon now is at minus infinity. And when we write the potential, we have something which looks like this. And when we have this type of potential in quantum mechanics, usually the type of boundary condition that we impose are either outgoing or ingoing. And if we look at the physics of the problem, then at infinity, we don't want anything to come inside our universe. So we impose outgoing, and at the horizon, we have ingoing. Now, you can show that the Reggie-Wheeler equation with this particular type of boundary condition is satisfied only for a discrete complex set of frequencies, which I will go to them in this way. And these are precisely what are called the black hole quasi-normal. So what we notice basically is that if you do a little bit of algebra, you can write the Reggie-Wheeler equation as the quantum Seider-Witten curve for an SU2 gauge theory with 3 fields. Okay. And in order to do that, you have to use a particular dictionary between the gauge theoretic framework and the black hole setup, which is summarized in this table. So this basically means that this Reggie-Wheeler equation also belongs to this type of operator, which we can study using this gauge theoretic approach. And for example, if you take this point of view, then you can systematically and in a very straightforward way write down, for example, the exact quantization condition for this black hole quasi-mechanics, which in this case it looks like this. Where this is the Nekrasov-Shatashvili free energy for the SU2 theory with free flavor. And as I was stressing earlier, this is a well-defined object that we know how to compute explicitly. And in order to make contact with black holes, we have to evaluate this quantity using this particular dictionary. And then indeed, you can show, for example, that the quasi-normal mode frequencies, which are obtained by imposing this quantization condition, indeed agree with several computations that were done before by Berti, Cardoso, and collaborators. Now, this was the example of the Schwarzschild black hole, but the same approach can actually also be generalized to a larger class of black hole, for example, to the Kerr solution. Okay, so in this case, instead of one equation, you have a set of 2 equations, but you can study both of them within this gauge theoretical framework. And the relevant gauge theory also in this case is the theory with 3 flavor. But the dictionary now is going to be different with respect to what we saw in the Schwarzschild example. And also an interesting point is, for example, when we want to study the extremal limit in the Kerr framework, from the point of view of the Seider-Witten theory, this has a natural interpretation in terms of the decoupling limit, where we go from the theory with 3 flavor down to the theory of with 2 flavor. And this allows us also to analyze this extremal limit in a very smooth way. And then another maybe nice consequence is the fact that by using this approach, you can get a very explicit and also exact form for the spheroidal eigenvalue, which characterize the angular part of the Chukowski equation. And these are essentially given by the Nekrasov-Shepashvili free energy evaluated at some particular, using some particular function. Now, these are the 2 examples that we worked out in detail, and these are 4-dimensional examples which are asymptotically applied. But there are also some preliminary results which indicate that this should also be possible to extend this to asymptotically ABS solution. It's just that in this case, the matter content of the gauge theory is going to be different. Instead of a theory with 3 flavors, we will have 4 flavors. And also this connection actually, so this is a particular subset of example, because so this connection recently was also extended to a much larger class of gravity diagram by these people here. And then and another interesting application is that you can actually compute several quantities that appear in this black hole analysis in a very explicit form. Like, for example, the finite frequency gradient body factor in this framework is nothing else that up to some factor, the Nekrasov-Shepashvili free energy, again, evaluated by using a particular dictionary. And a last point, which is also interesting, is that basically when you map this the problem to this supersymmetric gauge theory framework, you have some hidden symmetry which show up, and this is actually useful if you want to study, for example, stability in the context of Kerr. Okay, so let me now briefly conclude. So this geometric or gauge theoretic approach to spectral theory gives us some interesting new non-perturbative tools, which can actually be applied in various contexts, including, for example, the study of black holes. And it would be maybe interesting to see at which point we can push that, and what are the most interesting consequences. And okay, so thank you very much.
So thank you, Alba, for a very, very nice talk. Lots of people jumping in with questions. Andy.
Two related questions. Are you saying there's any relationship between these Seiberg-Witten curves of these gauge theories and the quasi-normal mode equations for the black holes, or they just happen to be the same equation? Is there some duality relating these systems, or you just found the same equation? And the second part of that question is, I mean, these are differential equations that we can only solve numerically, right? So finding them in it, is it helpful to find it in another system?
Okay, so the first part of the question, so we found it that it's the same equation. I don't know if there is a deep physical explanation, like why is it the n equal 3 or the n equal 4 theory which enter rather than another one. I don't know why is that, if there is a physical explanation for that. Yeah, what we found is that basically the equation is the same. So it's more a mathematical. And the second part of the question, yeah, is this. So the second part of the question was, what are the new insights that you can get using this approach, more or less, right? Yeah, so, well, for example, okay, so at the level of, if I insist on comparing with the numerics, which I think is great, for example, one point where the numerics is maybe a little bit hard is when you go to this extremal limit. And instead with this approach, this part you can do it very, very smoothly. But I guess my point is not really to compete with the numerics, which is and people are developing this in great details. but it's rather to give a new, maybe more analytical perspective, which can be useful, for example, to compute the gray body factor at finite frequency, which from this point of view, you can really obtain very explicitly, and then you can show that in the zero frequency limit you recover your result that you obtain something. And also this relation with this hidden symmetry that show up and is apparently useful for studying stability questions. This is also something that you don't get just by studying numerical distribution.
Okay.
And maybe more wisdom. That's fine. Thank you.
I had two questions. One was, I understand how to convert a Schrodinger problem to a spectral curve problem. How did you input into the Schrodinger problem the boundary conditions that are specific to quasi-normal modes? Was that part of the dictionary, or is that something natural to a spectral curve?
No, the spectral curve in the quantum Seiberg-Witten curve is an operator, so you can choose which boundary condition you want to impose, right? And for example, depending on which boundary condition you impose, you have a quantization of a certain cycle. Mm-hmm. For example, if you take the Kerr solution, okay, you know that you have two equations. You have the angular Czukowski and the radial Czukowski. And two have two different types of boundary conditions.
Right.
And the two are mapped basically to two different types of quantization.
I see. And my second question was, when you talk about stability, you specifically are talking about mode stability, not
yes.
the linear stability of the solution itself.
I'm talking about mode stability. Yes, that's at least this is what these people that I was mentioning were discussing.
Andy? Oh, I think you're muted.
Thanks for a very interesting talk. I don't really understand this connection between Schrodinger problems and the spectral curve. My questions are similar to Andy, but please allow me to ask them anyway. When is it that a Schrodinger problem can be mapped to an interesting curve you get out of super symmetric Yang-Mills theories? I mean, is there some general understanding of that, or is it just that it happened to work out for these black hole problems? I mean, it's quite miraculous to me. Go ahead, please, if you could. Is there any sort of understanding? Sorry to make you repeat this, but just in case, or is it just,
yeah? There are actually a much larger class of problems which can be studied in this way. So this is not just specific to this black hole example. There are like many problems in the higher order equation, even difference equation when you look in terms of relativistic integrable system and so on. So this case theoretic approach is quite general, and it's not just for this particular example.
I see.
And usually, if I have an operator and I want to see if I can study that by using this approach, I just see if I can connect that with one of these gauge theory, and then you can.
I see. So you just compare it with the list of all the gauge theory curves, and you see if they fit. Okay. And then, sorry, but again, did this allow you to get a analytic approximation in some way to, for example, the Kerr quasi-normal modes? Does it, in a practical way, help you?
Yes.
You might have said that. Yeah, go ahead.
What do you mean by practical?
Well, I mean, you may not do as well as the numerics in all detail or something, but as an approximation, does it help you just get a handle on the exact quasi-normal modes? Or what does it buy you just in a very pedestrian way?
Yeah, that is what I was already answering to Andy, for example. For example, the example, if you just want to stick to the numerics and compare with the numerics, you have the extreme and limit that where you can and yeah, it's essentially this. I would give the same answer.
Okay. Thank you.
Okay, so there are some more questions that people want to ask, but I think we need to move on to the discussion session, please. So let's thank Alba again.